All right, for when we are back, and whoops. Uh-oh. Here we go. Let's go ahead and zoom in. We are back, and we are about to go through our Pset 4 solutions. So I'm looking at 3 different systems with relaxation times, A, system B, system C, different means, or sample means, different values. So let's go ahead. I'm going to go ahead and start a new notebook here. And I'm just doing this mathematic. I can do this in R as well, but it's just calculations here. So the number of A measurements was equal to 49. X of A was 29 seconds. The standard deviation of A, or the sample standard deviation, was 1.8. And then number of B equals 14, small sample size. X of B equals 38. And standard deviation of B is equal to 5.6. What else? System C and C equals 27. XC equals 36. And standard sample deviation of C is equal to 3.1 seconds. All right. So calculate the 90, 95, and 99% confidence intervals for systems A, B, and C. So to do this, we're just going to have to use our function that we're going to have. Basically, it's going to be our mu is going to be equal to x bar plus or minus t alpha over 2 nu times standard deviation of whatever our x is over square root of n. So we're going to have to find this value because we already have this, and we have this. So we need to find t of, basically, so our alpha is, remember, is equal to our 1 minus the confidence interval percentage. So for 90, it's going to be t of 0.1, but it's divided by 2, so 0.05. For 95, it's going to be t of 0.025. And for 99, it's going to be t of 0.005. I believe that's correct, because 0.1 divided by. Excellent. So, but our nu is equal to n minus 1. For A, that value is always going to be infinity. But for the other values, it's going to change. So for C, nu of C is equal to 26. Nu of B is going to be equal to 13. And so we'll keep that there. So I'm going to do T of 05, and then inf, and then we're going to have equals this, T of 025 inf equals that, T of 005 inf equals this, T of 05 13 equals T 005 13, T 025 13 equals, and T of 005 13 equals this, T of 05 26 equals this, T of 025 26 equals this, and then T of 005 26 equals this. So let's find those numbers. And to do that, we're going to go ahead and pull up our PowerPoint. This is our T table here. We can zoom in a bit. So for example, actually we'll go ahead and pull this down a little bit, make it a little bit bigger. Exactly, and zoom in a little bit more. There we go. So 05 infinity is going to be 1.645. And we'll go down. 025 should be 1.96. We should all have that kind of memorized by now. 005, which is not as common, is going to be 2.576. All right. T05 13 is going to be 1.771. T of 025, 1.771, 2.160, and then T of 005, 3.021, 012. And then finally, let's go down to 26, 05, 1.706, and then T025 of 26, 2.056, and finally 2.779. There we go. So we can just do XA. Basically, I could do, let's see, instead of plus minus, I can do around. Around a delta. So I can do a value plus or minus, basically that value there. And then we can look at that numerically. So I can do around XA, and then I can do, comma, my T05 infinity times S of A divided by square root of N of A. So there we go. I can copy, and just replace this with 025. And then I could do this with 005 here and here. And we can see those values changing. Great. I can do the same thing now. I'm just going to copy it here. XB, SB, and B. And then I'm going to change the inf to my 13 value. And B. Oh, and I'm going to copy this here now. Because I'm just going to change this to 025 and then 005. And again, this is not to be mean. It's just to kind of make sure that we're very comfortable with these types of calculations. And XC, T05, 26. And then we're going to do SC and C. And then finally, boom, boom, 025. And then 005. There we go. We've got it. So let's see what the question asks. Did it. Boom. Now, let's look at some new data files. PS41, blah, 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 blah. And let's go ahead and calculate those. So what we're going to do is we're going to pull up some of our documents from my downloads. We're going to look at Pset 3. Let's open it in R always. But that's not the one we want. We want Pset 4 actually. Where are you, Pset 4? Here we go. So we're going to change. Let's go to files here. We are going to create. I don't know why I kept putting 4. We're going to set this as our working directory. So we're going to set this here. And set this right here. So let's do Control Enter, Control Enter. We're going to read our files 1, 2, 3, 1, 2, 3, and then find our confidence intervals. We'll just do what we did last time: 90%, 95, 99. Now for file 2, same thing, and we're already automatically getting those values based on our number of measurements here. So it's great to work with data. Fantastic. And then the last part of this problem set, prove the central limit theorem is true for a normal distribution, Poisson, and beta. Provide your R script. This is the same thing that we did in class. So let's look at a normal distribution, a Poisson, and a uniform, or a beta distribution, excuse me. So, or actually, what is it? What is it asking for? Poisson, beta. Yeah, normal, Poisson, and beta. And our central limit theorem is just basically saying that if we take samples and large enough samples and look at the distribution of the means of those samples, they will look Gaussian, despite the fact that their actual distribution does not look Gaussian. So you can see this is our distribution here for our uniform distribution. Actually, not the uniform distribution. That is going to look like our beta distribution. But when we sample this data, it's a uniform, as we increase the number of samples, and it'll get better and better. It looks more and more Gaussian, like we see here. And we can do the same thing for the 50, Poisson. And then we can do the same thing for our normal as well. So there you go. Same script like we did in class. Just make sure that we're clear. Beta, Poisson, normal distribution, and make sure you show that. So we'll see you in the next video. Peace at 5. Thanks. Bye.